Today's presentation is an introduction to thermal testing. Again, my name is Tom Resh. I'm an environmental test specialist, and if you have any questions or comments after this presentation, feel free to email me at tomvibetest@gmail.com. Today's topics are terminology and basic concepts that are used in thermal or temperature testing. What is thermal or temperature testing? Thermal or temperature testing is the simulation of the harsh thermal environments that an electronic or mechanical device would be exposed to during operation. Some examples of these harsh real-world thermal environments are a desert climate, which is relevant to our current Middle Eastern conflict, in which military hardware must be able to withstand the harsh, high-temp environments of a desert. Another example is a harsh, low-temperature environment, or low-temperature climate, for instance, a snowstorm. And also, let's say you wanted to go skiing and you had your cell phone with you. Your cell phone hopefully was tested to be able to withstand low temperature environments in order for you to be able to use it in case of an emergency or even for just miscellaneous use when you're out in a harsh cold environment. Another example would be the harsh environment of space. Your space vehicle, satellite, should be tested to be able to withstand the harsh environments that it would see in outer space. What is ramp rate? Ramp rate is expressed as degrees per minute. It is the slope of the temperature test graph. Finding ramp rates is very, very simple. It is just a simple division problem. We're going to go ahead and perform a problem to show you how to find your ramp rate when you have a temperature transition given to you and a time period for which this transition should occur. What is ramp rate? The ramp rate when the current temperature is 25 degrees Celsius and it is reduced to minus 45 degrees Celsius in 20 minutes. What is the ramp rate? First, we must find our total temperature that is transitioned. So we will go ahead and we will add 25 plus 45 because 25 degrees is 25 above 0 degrees and minus 45 is 45 degrees below 0 degrees. So you have 25 plus 45 equals 70. Next, we will go ahead and divide 70 by 20. This gives us a ramp rate of 3.5 degrees C per minute. This is the ramp rate for this current criteria given in this word problem. What is a soak time? A soak time is a duration of time that a system dwells at a single temperature set point. It is the plateau and the valley on a temperature test graph. Now, I keep mentioning a temperature test graph. Let's go ahead and look at a temperature test graph profile. Here is an example of a temperature test profile. This is typically what you will see, what you will be given to in a procedure or by an engineer to program into your test controller for your environmental test chamber. Here you have a set point of 25 degrees C. This is your initial temperature at which the chamber should be at before the test starts. And here you have your transition. Here is your slope, which is your ramp. And this ramp should occur per the spec in 5 minutes. So you have a temperature transition from 25 degrees C to 50 degrees C in 5 minutes. Now, if we go ahead and perform that simple division formula that we looked at previously, you would go ahead and you would find your 25 degree transition divided by your 5-minute ramp, which would give you 5 degrees per minute. So you would program into your test controller a ramp rate of 5 degrees per minute in order to satisfy this ramp criteria. And here you have a plateau. This is your soak duration, your dwell time at 50 degrees C, and your soak time is 1.5 hours. So here is your soak time for this plateau, this temperature dwell. And once again, here is another slope. This is a negative slope down to minus 50 degrees Celsius. So you have a transition from 50 degrees C to minus 50 degrees C, which is a total of transition of 100 degrees. And this is to be done in 20 minutes. And once again, you calculate your ramp rate by taking your temperature, which is 100, over the ramp time, which is 20 minutes, and you would end up with 5 degrees C per minute once again. So your ramp rate that you would program into your controller would be 5 degrees C per minute in order to have a 100-degree transition in 20 minutes. And here you have a valley. This is another temperature dwell period, and your soak time is 1.5 hours. And once again, you have a ramp back up to ambient. And this should occur in 15 minutes. And once again, you have 50 and you have 25 above zero, which gives you 75 degrees. Over 15 minutes would give you a ramp rate of 5 degrees per minute, 5 degrees C per minute. And that is the ramp rate that you should program into your controller for this ramp. Now, this is considered a cycle. When you have a temperature, when you go hot and cold or cold then hot, that is considered one cycle, because it's just like considering if you're looking at a sine wave, you have a positive and then you have a negative. You have a peak and then you have a valley. It's the same principle. This is considered one cycle. What is GSOAK? GSOAK stands for Guaranteed Soak. This is a feature of many temperature controllers for test chambers. It allows you to set a tolerance that if the temperature deviates from this tolerance, your soak time countdown stops. This guarantees that your unit or system soaks for a certain period of time at a given temperature, and a deviation from that temperature, which let's say you put in a 5-degree tolerance. If your temperature deviates from that 5-degree tolerance, it would stop your soak time countdown, and it would not continue until your set point temperature is once again achieved, or once again your air temperature gets within the tolerance that you set for your guaranteed soak feature in your test controller. Okay, now we're going to explain two different types of temperature tests that are often performed: manual and programmed tests. Now, in a manual test, you set the set points and rep rates manually. So let's say you want to go to 50 degrees, you manually input 50 degrees, and then you allow it to ramp up and soak at your 50 degrees C, and then you would manually ramp the temperature down to your next temperature. Let's say it's minus 50 degrees C, and then once again you would wait for it to soak for a given period of time, whatever your desired soak time is, and then once again you would go and change your set point again. So this is a manual change of set points. It is not automated. This is one type of test that people do. It's mainly the reason why manual tests are performed is because of limitation on resources. Let's say a test lab, they might not have sophisticated control systems. They just have, let's say for instance, a manual watt-low controller where you would just put your set point in and the chamber would just go there. So manual tests are usually performed because of a limitation on test equipment available. But sometimes engineers want to run tests manually so that they can change the temperature to whatever they want, whenever they want, in order to troubleshoot an issue with their system. Now, the other type of test that is set up is a programmed automated test profile. Programmed profiles perform preset ramp rates and set points and cycle loops. Now, what is a loop? A loop is a repeat of a cycle. Many controllers have a loop feature, which allows you to input a number of loops and the number of loops will determine how many times you'll repeat a cycle. So let's say you have a cycle that goes from plus 50 to minus 50. Now, instead of inputting this cycle multiple times, let's say you wanted to do it 10 times, instead of creating 10 copies of the cycle, a controller would allow you to input 10 loops. And therefore, once the cycle completes, it would repeat the same cycle again for a total of 10 times. This cleans up your test profiles, and it also decreases the amount of time for setup by the controller allowing you to input loops into your test profile. What is a thermocouple? A thermocouple is two dissimilar metal wires that are welded together to create a junction. Now, this junction of two dissimilar metals, which are conductors, produces a voltage, which is proportional to the temperature at which the junction is exposed to. Again reiterated, thermocouple produces a voltage that is proportional to the temperature at the thermocouple junction. Now, there are many different types of thermocouples that have different temperature ranges and are used for different applications. Let's go ahead and look at a table that will provide us information on some of the major types of thermocouples that are used and their continuous and short-term temperature ranges. In this column, you have your various types of thermocouples. In this column, you have your temperature range for continuous use, continuous operation for each type of thermocouple. And here you have your short-term use for each short-term use temperature range for each type of thermocouple. And this tolerance tells you the tolerance or how accurate it is for a certain temperature range for each type of thermocouple. Now you see here, we're going to go ahead and just compare each of these to the continuous temperature range, and this will help shed light on which type of thermocouple you would use for temperature testing. Now here you have a K-type, which has a 0 to 1100 continuous operation temperature range. So obviously for a K-type thermocouple, you would want to use it for high temperature applications. And here you have a J-type thermocouple, which has a temperature range of 0 to 750 degrees Celsius. Once again, this is a good thermocouple for high temperature applications. And here you have a N-type thermocouple, which once again is for high temperature applications. And you have R, which has a slightly higher temperature range for its continuous use. And this is once again really good for your super hot temperature applications. And here you have a S-type thermocouple, which has a temperature range of 0 to 1600. So just like the R, it is slightly higher than the K, or the K and the N thermocouples, and can be used for slightly higher temperatures. And here you have a B-type thermocouple, which is strictly used only for high temperature applications from 200 degrees C to 1700 degrees Celsius. Here you have a T-type thermocouple, which has a temperature range of minus 185 C to plus 300 degrees C. And here you have your E-type thermocouple, which has a temperature range from 0 to 800 degrees C. Now, out of all of these thermocouples, which type do you think would be commonly used in temperature testing? I'm sure you picked the T-type thermocouple because of its range from minus 185 to plus 300 degrees C. In thermal testing, you will have low and high temperature set points. So therefore, you would want to have a thermocouple that has a operating range that goes to a low temperature and goes to a high temperature. And this temperature range is sufficient for just about every type of thermal test that you would encounter when performing environmental thermal tests on hardware. And it also, if you look here it has a very, very high accuracy, very, very tight tolerance at temperature ranges that would commonly be used in thermal testing on hardware. So for thermal testing, typically you would use a T-type thermocouple. Okay, here is what the heart of temperature testing, your thermal test chamber. This is an example of an SE series thermotron chamber. This thermal chamber is used to cycle your temperatures from high temperatures to low temperatures, or from low temperatures to high temperatures. There are two types of refrigeration that can be used for this thermal test chamber. It could use a mechanical refrigeration system known as a cascade refrigeration system, which typically allows cooling down to -40 to 65 degrees Celsius. It all depends on the size and the performance capacity of the refrigeration machine pack for that chamber. Another form of refrigeration is liquid nitrogen, LN2, which allows temperatures to exceed the limitations of the mechanical refrigeration system. It will allow you to go to temperatures as low as -150 degrees Celsius. So you could use these two systems separately, or you could use them in tandem together. You could have your cascade system get you to -65 C or -40 degrees C, and once you've reached the limitation of your mechanical refrigeration system, you could turn on your LN2, and turn off your cascade system, and it would allow you to achieve your temperatures that are beyond that go past the limitations of a mechanical refrigeration system. So depending on your application, you could either use a cascade refrigeration system, an LN2 system, or a combination of both. Now we are going to discuss control strategy basics. Now, when I say control, I'm talking about thermocouple control location. Ultimately, it's dependent upon your customer requirements, where your customer wants you to put your thermocouple. But typically, for passive units, you would use air control, and for high-powered or high-output test specimen, you would use product temp control. Product temp control is the placement of a controlled thermocouple on the unit itself. Now, product temp control is fine if you only have one unit, but if you are performing batch testing where you have multiple units in one chamber, product temp control would not be practical because you'd only be able to control to one of your test units. Ideally, you would want to use a cold plate for your more higher output, high-powered test specimen. A cold plate would allow you to maintain a safe operating temperature for your high-powered test specimen, and it would not require you to have to use product temp control. You could use air control. This is great because it would eliminate the need to have monitor or response thermocouples on every single unit inside the chamber. This would minimize your setup time and minimize the amount of data you would need to collect. So it would eliminate unnecessary paperwork, and it would speed up setup time by having cold plates for batch testing setups. Okay, here are some other considerations when performing thermal tests. Moisture. It is electronics' worst nightmare. If you have moisture present inside your chamber, you can damage the unit you're testing. You can create an unnecessary, unwanted environment inside of your chamber if it is not set up correctly. Typically, you would want to have a purge air system. Moisture is attracted to colder surfaces. So when you run your chamber down to a cold temperature, you're pulling in all the moisture. It acts as a vacuum and pulls in a vacuum for moisture, and pulls in all the moisture in the surrounding air around the chamber, inside the chamber. Now when you heat up the chamber, you are going to have moisture condensation all over your test hardware. And if you have exposed electronic cards or other moisture sensitive devices, you could destroy them unnecessarily because you did not use purge air. Purge air creates a positive pressure inside of the chamber, which prevents moisture from migrating into your chamber. So usually you will always want to use purge air when performing thermal tests. Another consideration when setting up thermal tests is auxiliaries. A lot of test controllers, more sophisticated test controllers, allow you to set up circuits that turn on and turn off devices during certain set points or certain intervals within a test profile. This is extremely useful because you could set up auxiliary circuits to turn on units automatically or turn on functional test equipment automatically so that you could automate your test. Auxiliaries can also be used to open and close solenoids. Let's say for a solenoid that would control the input of LN2 into a chamber. So you could set up at a certain interval for an auxiliary that would allow the solenoid to open up and allow LN2 into your test chamber. Today we discussed terminology and basic concepts in thermal testing. This was just a brief summary of some of the different issues, different terms, and different concepts that you would encounter in thermal testing. Thanks for watching. Again, my name is Tom Resh. I'm an environmental test specialist, and if you have any questions or comments regarding this presentation, feel free to email me at tomvibetest@gmail.com. Thanks again for watching.